We are going to continue on talking about exponential applications. This is part 2. Our goal is to use exponential functions to solve exponential growth and decay problems. So recall exponential growth. So if we have something that's continually growing, such as a population, we have the equation P of t equals P naught e to the kt, and all of those letters that you see are defined below, where P of t is the amount at time t, P naught is the starting amount, K is the growth rate. Remember to work with it as a decimal. T is the amount of time, and T and K should have the same units. Also recall something we talked about a couple lessons back of continuous compounding. This is where we were putting money into an account and it was compounding continuously, always growing, always growing, always growing. You're getting interest. So notice that the equation we talked about there was A is equal to P e to the RT, where A was the amount in the account after time T, P was the initial, R was our interest rate, and T was the amount of time. And we have the same thing here. P of t is the total amount after time t, P naught is the initial, K is our growth rate, which if you have an account that's continually growing with the annual interest rate, it's the same as the growth rate times t. Okay, so we're going to do an application problem with continuous compounding. So suppose you initially deposit $7,000 into an account with an annual interest rate of 3.2% compounding continuously. So find the exponential growth / compound interest function. So it's both here. It's exponential growth because it's continuing to grow, and it's also specifically related to compound interest. So in our problem, we're initially depositing $7,000. So this is our starting amount, okay, or P. With an annual interest rate of 3.2%, so as a decimal, that's 0.032, and it's compounding continuously, which tells us we're using exponential growth. So we have everything we need. So we have P of t is equal to 7,000, e to the k, which is 0.032, times t. So this will allow us to get the amount in the account after t, where t is in years, okay? Part B, find the doubling time, capital T, round to one decimal place. So doubling time is related by K times capital T, ln 2. We can solve this right away for K and say that T is equal to ln 2 over K. So we have ln 2 over 0.032. So we can plug that into our calculator. So ln 2, hit enter, divided by 0.032, and this is 21.6608. It says to round to one decimal place, so we're rounding the first 6. We look next door, the number next to it is bigger than 5, so this is 21.7 years. Okay. The other thing I should note on this is if you forget how the rate and the doubling time are related, so we started with 7,000, you could use 14,000 is equal to 7,000 e to the 0.032 times t, and you'll end up at the same spot. Part C, find the amount in the account after 5 years. Round your answer to the nearest cent. So after 5 years means t is equal to 5. Okay, so we have P of 5 is equal to 7,000 e to the 0.032 times 5. So if we plug this into our calculator, so 7,000, locate your e to the power of x, 0.032 times 5, close the parentheses, and we get 8,214.576097. Okay, cents, remember that a cent is 1/100th of a dollar, so when you're rounding to the nearest cent, you're rounding the hundredths place, or think of it like if you go to McDonald's and your total is $4.38. It's point, and then it's got 2 numbers after the decimal, okay? So we look next door, the number next to it is 5 or greater. So after 5 years in this particular account, we would have $8,214.58. So next we're going to talk about exponential decay. So continuous decay uses the equation. It's really similar to growth, except we have negative K, since whatever we're dealing with is decreasing, okay, continuously decreasing. So P of time is the amount after time t, P naught is the starting amount, K is our rate of decay, which again we'll use as a decimal, T is the amount of time, and T and K need to be in the same units. So half-life, if we know the decay rate or the half-life T, they are related by KT is equal to ln of 2. So if you're thinking this looks familiar, you are absolutely right. This is the same way that we find doubling time if we know K. Okay, but remember that this can go the other way, whereas if we know the half-life, we can find K from this equation, which is exactly what we'll need for our next example. Okay, so a radioactive element, carbon-14, has a half-life of 5,750 years. A scientist determined that the bones from a mastodon had lost 80.8% of their carbon-14. How old were the bones at the time they were discovered? Round to the nearest integer. So in this case, we're talking about exponential decay because this is something that's continuously decreasing or going down. Okay, so if we're starting to build our equation, we would have P of t is equal to P naught e to the negative k t. Using the first part, so we don't have k, but since we know the half-life, we can use kt is equal to ln 2 and solve for k. So the first step in this is to find k, and then we'll talk about what that 80.8% means in just a minute. Okay. So K is what we're solving for. We have a half-life of 5,750 years is equal to ln 2. So we divide both sides by 5,750. And we have K is equal to ln 2 over 5,750. And I would just leave it like this because we are going to need to use K. And as I mentioned previously, if you round this, that rounding error is going to carry through the rest of the problem. So make sure you just leave it like this. Okay. So now what we have is we have P of t is equal to P naught e to the negative k, which is negative ln 2 over 5,750 times t. Okay. So now we need to determine what's happening with this 80.8% of their carbon-14. So one way to do this is to assume that we're starting with 100%. So this could mean that P naught is 1. So 100% as a decimal is just 1. So after, we don't know how long, that's what we're trying to find, so we're solving for t, but we know that P of t is 1 minus 80.8% is 0.808. Okay, so if it's lost 80.8%, if we take 1 minus 8 or 0.808, it gives us 0.192 as a percent. That's 19.2%. So if it's lost 80.8%, that means that 19.2% is remaining, and that's the amount that we're actually going to need in our equation. Okay. Remember when we talked about like discounts, if something was 20% off, you're actually paying 80% of the original. Well, here, if the scientists determined that the bones had lost 80.8% of their carbon-14, that means that 19.2% are remaining, okay? So we don't actually need to know the original amount here, or you can assume it's 1,000. You can pick any number you want. It's still going to end up the same in the end, okay? So, and now what we have in order to solve for t, so we have P naught we said is 1, okay? P of t is 0.192. We have k, so now we're able to solve for t. So what this looks like is we have 0.192 equals 1 e to the k, which is ln 2 over e to the negative k times t. Okay. So if we divide both sides by 1, 0.192 is equal to e to the negative ln 2 over 5,750 times t. In order to solve this exponential equation, we use logarithms. So I'm going to take the ln of both sides to get ln of 0.192 is equal to the ln of e to the negative ln 2 over 5,750t. Okay. Using the power rule, we can bring the exponent in front. So we have ln of 0.192 is equal to negative ln 2 over 5,570 t, and then we have ln of e, which ln of e is just 1. So now we need to solve for t. So there's a couple different ways you can do this. You can divide both sides by negative ln 2 over 5,570. If you wanted to, you could start out by multiplying 5,750 to both sides and then divide it by negative ln 2. Whatever you decide is completely up to you. Okay, what I'm going to do is I'm going to show you that it's okay, that you can just take Okay, negative ln 2 divided by, okay, so t is equal to ln of 0.192 divided by negative ln of 2 divided by 5,750. Okay, so this is what we put into our calculator. So we put ln of 0.192 divided by negative ln 2 divided by 5,750. Oops, hold on. So let's deal with this compound fraction actually first before we do that. So we have a fraction within a fraction. We can take this and take 5,750 to the top and bottom to get ln of 0.192 times 5,750 divided by negative ln 2. Okay, so this might be a little bit better to put in. So we're going to take ln of 0.192 times 5,750, hit enter, and divide it by negative ln of 2. Okay. And we get 13,689.7252. Okay, so now the problem says to round to the nearest integer, or really to the nearest year. With that, we're deciding if this is closer to 13,689 or 13,690. Okay, the nearest integer is the ones place. We look next door. The number next to it is 5 or greater. So this is 13,690. So the bones were about 13,690 years old when they were found. Thank you for watching. If you have any questions, feel free to reach out to me.